Welcome to the Deep Dive. Our mission today, well, it's to create the ultimate shortcut to mastering the essential chemistry of nitrogen.
Yep.
We're taking a deep dive into the paradox of this element, distilling every required concept, definition, and reaction pathway you're going to need.
That's right. And nitrogen really is the ultimate chemical contradiction. I mean, it makes up 78% of the air, and it's famously inert, right?
Right, unreacted.
But its compounds are absolutely essential for life. They're the backbone of our global food supply through fertilizers, but at the same time, they're also major environmental hazards.
Yeah, driving pollution and climate issues.
Exactly.
So we're going to untangle all this complexity. We'll follow a clear path for you, starting with that duality, agriculture versus pollution. Then we'll get into the structure, why N2 gas is so unreactive. After that, ammonia and ammonium ions.
And finally, we'll hit the big one, the critical role of nitrogen oxides, that's NOx, as atmospheric pollutants.
Okay, so let's start with that duality, right down at ground level. Ammonia, NH3.
Right. Ammonia is the starting point for pretty much all essential fertilizers. Ammonium chloride, nitrate, phosphate, sulfate, all of them.
And these are just so crucial because plants need soluble nitrates, the NO3 minus ion, to absorb through their roots. That's how they make proteins.
Yeah, and when you harvest crops, you're literally pulling that nitrogen out of the soil for good.
So you have to put it back in, artificially, usually.
And this is where the problem starts, because these fertilizers have to be water soluble, right? So when farmers maybe use a little too much, the excess nitrates just leach out of the soil and get into our waterways. And that triggers a really destructive process called eutrophication.
Okay, eutrophication. I think a lot of us have heard the term, but what's actually happening?
Yeah.
What's the mechanism that makes it so damaging?
It's like a devastating chemical feedback loop. First, the nitrates hit the water, and they cause this huge, rapid bloom of algae right on the surface.
Okay, so you get that green layer on top of the lake or river.
Exactly. And that algae layer blocks all the sunlight from getting to the plant life below it. So naturally, those plants die.
So now we have a massive amount of dead organic material just sinking to the bottom.
Exactly. And this is the fatal step. Bacteria in the water, they start to feed on all that dead plant matter, and they multiply. I mean, they multiply rapidly.
Okay.
And here's the key. These bacteria, as they multiply, they use up the dissolved oxygen in the water way, way faster than it can be replaced.
And the fish, they need that oxygen.
The fish, other aquatic life, they suffocate. The entire ecosystem just collapses.
Wow. It's like a chemical chain reaction leading to total ecological collapse.
And there are also human health concerns, right? The whole debate around nitrates in drinking water.
Absolutely. There are links, or at least concerns, about blue baby syndrome in infants and even some stomach cancers. So the takeaway here is really that timing and quantity are everything.
So for farmers, the solution is applying just the right amount, the most economical amount, at the right time. Exactly. You want to minimize the excess that can leach into the water table.
Okay, so let's move from the soil up into the air and talk about the foundation of this element. Nitrogen gas, N2.
Right. It's a non-metallic element, group 15, exists as a diatomic molecule.
And it makes up 78% of the air we're breathing right now.
And to understand why it's so unreactive, why it's just diluting our oxygen instead of reacting with everything, you have to visualize the bond. Nitrogen atoms form a triple covalent bond. N, 3 lines N.
And we're not just talking a strong bond. This is one of the strongest bonds in all of chemistry.
Oh, it's exceptionally strong. We measure its bond energy at nearly 1,000 kilojoules per mole.
1,000, wow.
So to put that in perspective, you need a massive, almost instantaneous injection of energy just to split those two atoms apart.
Which is why N2 only reacts under really extreme conditions.
Exactly.
But nature, of course, finds a way to supply that energy. And this connects its inertness to the entire global nitrogen cycle. Lightning strikes.
That's the one. Lightning provides that huge activation energy for atmospheric nitrogen and oxygen to react, forming nitrogen oxide, the NOx gases.
Right. And we can track the oxidation state of the nitrogen atom here.
We can. It goes from 0 in N2 gas up to +2 in nitrogen oxide, or NO. Then it gets oxidized again to +4 in nitrogen oxide, NO2.
And that NO2 doesn't just hang around in the air, does it?
No, that NO2 is the key intermediate. It dissolves in water droplets and clouds, reacts with more oxygen, and forms dilute nitric acid, HNO3.
And the nitrogen is now at +5.
All the way up to +5, and that's the whole point. This is how nature turns unreactive, insoluble N2 gas into soluble nitrate ions that plants can actually absorb.
Amazing. Okay, so that brings us perfectly to ammonia, NH3,
Mm.
probably the most important compound. It's unique, right? It's the only common alkaline gas.
It is. The classic test is that it turns damp red litmus paper blue.
And its alkalinity is completely dictated by its structure.
Completely. The ammonia molecule has a triangular pyramidal shape, and that's because the nitrogen atom forms 3 covalent bonds with hydrogens, but it keeps 1 lone pair of electrons for itself.
That lone pair is the key to everything, isn't it? It acts almost like a chemical hook.
That's a great way to put it. It's an available donor site. So when ammonia meets an H+ ion, a proton from an acid, the nitrogen atom donates that lone pair to the proton, forming a special kind of bond. We call it a coordinate bond, or sometimes a dative covalent bond.
And the result is the ammonium ion, NH4+.
Correct.
And that ion, the NH4+ ion, gives us some really great evidence about charge, right?
It really does, because after that ion forms, if you measure the bonds, you find that all 4 of the NH bonds are exactly the same length.
Even the one that was just formed from the lone pair.
Even that one. And that's the proof that the positive charge isn't stuck on the one hydrogen that joined. It's spread evenly across the entire ion, making all 4 bonds identical.
So that donation of the lone pair is what defines ammonia as a weak base. It's a Bronsted-Lowry base because it's a proton acceptor.
And we can see its weakness when we put it in water. It sets up an equilibrium. You get NH3 plus water in equilibrium with NH4 plus and hydroxide ions OH minus.
But it's a weak base, so that equilibrium...
It lies far to the left. Very few ammonia molecules actually react, so you get a low concentration of hydroxide ions. The solution is only weakly alkaline.
We can actually use that basic nature to our advantage, like to make ammonia gas in the lab or test for ammonium salts.
Yep, the classic method. You just heat an ammonium salt, like solid ammonium chloride, with a solid base, something like calcium hydroxide.
So what's the mechanism there? It's a displacement, right?
It's a simple proton displacement. The base provides hydroxide ions, which are strong proton acceptors. They basically steal a proton from the ammonium ion, which is acting as the weak acid here.
So the strong base just knocks the ammonia molecule right out of the salt.
Pretty much. And you're left with water, a calcium salt, and you get the release of ammonia gas.
Which, of course, we test for with damp red litmus paper.
And it turns blue.
Perfect. Okay, let's pivot back to those high-energy reactions we mentioned earlier and talk about nitrogen oxides in the atmosphere.
Right. So we said the natural source is lightning, provides extreme energy. The human-made source works on the exact same principle.
High temperature and pressure inside a car engine.
Exactly. The air, which is a mix of N2 and O2, gets compressed and ignited. That's enough energy to make them react, forming NO and NO2.
And this link is just fascinating to me. Whether it's a lightning bolt or a car's piston firing, the fundamental chemistry is the same. You need massive energy to split that triple bond.
And these NOx gases that are released, they pollute the atmosphere in 2 main ways.
The first one is pretty direct, right?
Yeah, the first is a direct contribution to acid rain. The NO2 dissolves in water droplets in the air and forms nitric acid. Simple as that.
But the second way is, it's more insidious. Nitrogen oxides act as catalysts to form the other main component of acid rain.
Sulfuric acid. From sulfur dioxide, SO2. This is the really critical insight.
So how does that work? How is it a catalyst?
Okay, so it's a 2-step cycle. First, an NO2 molecule oxidizes an SO2 molecule. You get sulfur trioxide, SO3, and the NO2 becomes NO.
Okay, so the NO2 is used up.
For a moment, but then that NO is instantly reoxidized by oxygen in the air, and it turns right back into NO2.
So the catalyst is regenerated.
It's regenerated, and it's ready to go oxidize another SO2 molecule. Meanwhile, the SO3 that was formed reacts with water to make sulfuric acid.
So even a small amount of NOx can create a huge amount of acid rain over time.
Exactly. It just massively accelerates the rate.
And this whole atmospheric reaction system is also what's responsible for photochemical smog.
Yep. You have your primary pollutants, which are things given off directly from cars like the NOx we've been talking about, and VOCs, volatile organic compounds from unburnt fuel.
And then you get secondary pollutants,
which are formed from reactions in the atmosphere. And smog gets triggered when those VOCs react with the nitrogen oxides in the presence of sunlight.
That's the photochemical part.
That's the photochemical part. And this whole mess creates really harmful secondary pollutants like something called peroxyacetyl nitrate, or PAN.
And PAN is nasty stuff.
Oh, yeah. It attacks your eyes, your lungs, and it even damages plant life. It's the trifecta of air pollution driven by nitrogen oxides.
So given that cars are such a major source, the chemical solution is the catalytic converter. How does that actually work?
Well, it basically reverses the unwanted reaction. You have a hot catalyst, usually platinum or palladium, in the exhaust system.
Okay.
And as the hot exhaust gases pass over it, the catalyst helps reduce the nitrogen oxides back into harmless, inert nitrogen gas.
And it does that by using another pollutant, right?
It does. It facilitates a redox reaction. A really common one is converting harmful carbon monoxide, CO, and nitrogen oxide, NO, into benign carbon dioxide, CO2, and harmless nitrogen gas, N2.
That's a perfect application of redox chemistry.
It is. The nitrogen in NO goes from an oxidation state of +2 back down to 0 in N2. That's reduction.
And the carbon in CO is oxidized from +2 up to +4 in CO2. The catalyst just makes that electron transfer happen quickly and cleanly.
So just to recap the core concepts for you, the fundamental inertia of nitrogen, why it's so unreactive, is all down to the incredibly high bond energy of its triple bond.
Right. And ammonia's lone pair of electrons, that dictates its basicity and its triangular pyramidal shape.
Right.
And it lets it form that ammonium ion where all 4 bonds are identical.
And finally, those nitrogen oxides. They're formed wherever you find high energy, be it lightning or car engines, and they are dangerous pollutants that cause acid rain both directly and by acting as a catalyst.
And they're the key ingredients for photochemical smog.
And when you look at it all together, you see that every chemical consequence, from the life-giving necessity of fertilizer to the catastrophic damage of acid rain, it can all be traced back to the energy needed to break or make that single triple bond.
It really raises an important question for you to consider, doesn't it? If fundamental chemistry dictates that we need enormous amounts of energy to create the useful nitrogen compounds we rely on, are we just doomed to always pay an environmental cost in the form of pollutants? Or can clever chemical engineering, like we see with the catalytic converter, continue to outsmart nature? Thank you for joining us for this deep dive.